All right. Well, thanks everyone for having me. Thank you to the LISA organizers and to the workshop organizers for inviting me. I want to talk about Space ROS, and to give you a little bit of background about the project itself. Like this, to give you a little bit background about myself first. I'm a principal computer scientist working for KBR at NASA Ames. And I'm the software lead for the Lunar Command and Control Interoperability Project, where we are using Space ROS. I'm also the technical lead of Copilot and Ogma, which are assurance tools for flight and robotic systems. And we are using Space ROS as well as F Prime and CFS. And I'm also the maintainer of ICOS, which is a tool for static analysis that I'll be talking about a little bit. I want to make it very clear that even though I mentioned some people throughout the presentation, and I also mentioned some organizations, is merely to give credit to people, but I don't speak on behalf of anybody, and I don't mean to represent that they are endorsing this presentation or this message. So I'm going to tell you why Space ROS came to be, what problems it tries to address, where we are today, what Space ROS really is, and where we are at the moment, and also where Space ROS is going in the future. I don't think I have to try really hard to convince you that the space industry is growing. We're seeing a boom in the market, in the industry. And robotics is going to be key for long-term space operations. And robots are in space. We have been deploying robots for decades. And they're not just the rovers or the helicopter. You know, robots are manipulators, and there's humanoid robots, and there's mobility systems and spacecraft, and there's landers, and they're kind of everywhere. And one of the problems that we're finding in these systems is that the complexity that they have today compared to the complexity that they had 5 decades ago has increased in terms of orders of magnitude. The complexity of the systems themselves and the missions that we're accomplishing has increased. The complexity of the software that we're running has increased, and also the complexity of the analysis. The processes are more sophisticated and so on. So there's a need for reuse. And this is a similar tendency that you will see in other systems. For example, CFS is a modular system that tries to, in some way, I don't speak for them, but I believe one of the core ideas that it tries to be modular and reusable. The same thing is true for F Prime, that it tries to facilitate reusability. And the same is true for ROS, the Robot Operating System. So ROS, for those of you who may be unfamiliar, stands for the Robot Operating System. And it's not really an OS so much as perhaps a software stack or framework that contains components that can be reused, as well as APIs and abstraction layers for the OS and multiple functions, and development tools and deployment tools and so on. And there are components, reusable components in ROS for visualization and for perception and communication and computer vision and navigation and so on. If you've interacted with robotic systems on Earth, which you must have, unless you live in a bubble, you've probably interacted with ROS in some way. There are hundreds of ROS companies, if not more, currently in operation. And ROS is kind of everywhere. And ROS has been deployed. So there have been robots flying that use ROS, famously Robonaut 2 and Astrobe. I believe, I'm not sure that they use ROS 1, but that Astrobe is moving to ROS 2. So under the hood, kind of the functions that ROS provides are similar to what you will see in other systems like the ones that we've talked about today. There's an application layer. ROS components or applications are called nodes, and they sit on top of a client layer that abstracts functions of the OS and communication. And under the hood, there's DDS, which is the communication system that is used for different ROS nodes to send messages across. And then all of that sits on top of, you can run this on Linux or Windows or different OSs. And this is not very dissimilar from what you will find, say, in CFS, right? At the top, you have applications instead of nodes, and then you have an abstraction layers that implement functions for flight, together with abstractions of the OS and communications and so on. Of course, the details are different. The programming languages that you use are also different in general, but kind of the ideas, if you distance yourself enough, are similar. So what is Space ROS? Space ROS is an open source robotics framework to develop flight quality robotic and autonomous space systems. That's the gist of it. That's the goal. And if you zoom into what that means, we seek to provide a space certifiable and reusable framework. We want to facilitate reuse across missions. We want to facilitate, like, shorten the time to market and the development cost. There's a lot of attention being paid to certification, even though we cannot really certify Space ROS at a specific level, say, because it doesn't really work that way. We can facilitate that missions could use Space ROS and then get Space ROS or their particular use of Space ROS to meet specific requirements. Space ROS provides artifacts that facilitate creating robotic systems for space. Even though it is a community project, it is open. We have participation from all over the world, including people from other space agencies. Space ROS, there's been a lot of interaction with people working with NASA requirements so that it is relatively aligned with the processes at NASA and is easy to go through those processes. But one thing we've found through doing that is that there's a lot of similarity between the processes that we follow and the processes that other people follow. So it's very easy to use Space ROS for other domains. And we've seen people push it to the point of considering using Space ROS for the agricultural domain. But it could be used by other agencies potentially, or it could be used by others. And as I said, it's to facilitate rapid development. The idea is that you should be able to prepare a system for space operation faster than you would otherwise. And it is a community project. It is an open community. It is developed as open source. The community meetings are open. People can participate, join as they please. And now, the way that I like to see Space ROS as a project is kind of as 4 pillars, right? There's Space ROS, the committees, the people involved, and how they are working on these things. Then there's the technology itself. There's an element of infrastructure that I'm not going to go into a lot of detail. And then there's the community surrounding Space ROS. With respect to the committees, Space ROS started, or at the beginning, it was funded through an ACO. And this was between STMD and Blue Origin. And at the end of the ACO, OSRF, the Open Source Robotics Foundation, passed the baton to Picnic Robotics to lead Space ROS. And they've been leading the planning and technical committees. And Picnic, you may know from SBIRs and other projects with JSC, and I believe they have also projects with DoD and so on. But Space ROS is a community project. There's a lot of people from many organizations. I want to make it very clear that when I mention these organizations, I'm not claiming that the organizations back Space ROS or they endorse it or that Space ROS endorses anybody. Is merely a testament to the variety of people that we have seen attend the meetings and participate in the discussions and so on. And as I said, we've seen people working in the agricultural domain. We've seen people working on space. We've seen people working on airspace, kind of everywhere. People who are not working on any of those domains. And now, when it comes to the technology, the piece of software that you actually download and use, and where you can try on your machine, there's a few elements to Space ROS, right? Space ROS is bundled as a Docker image. So the way that it works is that there's a selection of packages and versions of packages that are pinned in Space ROS and given to users as a Docker image. So you can start immediately by downloading that image and running it inside or launching that image. There's also sample applications. There's simulation tools and simulation assets. There's VMV tools. There's a dashboard, which is an extension or a plugin for VS Code. And then I'm also going to talk about something we've started doing on process compliance tools. So as I said, there's the easiest way to get started with Space ROS is just Docker pull of the image from the Docker Hub. It's osrf/Space ROS, and or Docker run, and you're in, right? You're in Space ROS. So you have a set of components available and installed, and a set of tools that will facilitate provide an assurance for Space ROS. By the way, I don't see the chat while I'm presenting. If there's anything that I should pay attention to or anything that you guys want to comment on, please go ahead and unmute yourself, or if somebody could help moderate, I'd appreciate it.
Ezra basically made a comment about Picnic is basically in the chat saying has a number of ongoing ROS-based SBIR Space 1, 2, and 2E, where we are working on adopting Space ROS to help support the notion of that Space ROS is ready for prime time and we should be moving forward for qualification. So I think it's not a question so much as a statement of intent.
Mm-hmm. Thanks.
Sure.
And this image, this Docker image that is being published in the Docker Hub, is being published every 3 months. And I believe since we started doing this more than a year ago, we've actually never missed a release, even by a day. Like we've always published on time. And for me, this is a testament to the message that we're trying to send to the community, which is, even though this is a community project and everybody's welcome to participate, we put reliability ahead, and we want not just the software to be reliable, but the process to be trustworthy. We want people to understand that we're seeking to produce a framework and a set of tools that you can trust, and a process that you can trust. And that cadence, that fixed cadence, I think is a good message and a good testament to that. And together with this base image that includes the packages and includes the tools, and I'll talk a little bit more about the tools that are included, there's also demos. Currently in the repo, we have a few, most notably are the Curiosity rover demo, which is connected to Gazebo, and then the Canadarm demo, also running in Gazebo. But one of the things that we did recently is that, well, I'll just say before I move on, that you can very quickly build these tools on top of the image, the base image, and run them on your machine. There's a documentation file, and it's just a couple of build commands that you run on different paths, and then you have these things running on your machine. And everything's built on top of Docker, so all the dependencies that you have to install are downloaded for you. We've made a big effort in trying to make that path towards having a full simulation and a full system running relatively painless. And I was going to say, one of the things that happened recently is that we had a NASA Spark crowdsourcing project together with Evan Lasky. And what we asked the community, this is not within NASA or even within the participants of Space ROS, but this was a message to the broader ROS community and open source community. We wanted to improve the simulations. We wanted to improve the fidelity of the simulations. We wanted to connect Space ROS to existing data sets about different moons, different planets. And we asked the community to send their submissions to the project. And we expected maybe 7 submissions. We've received 30 submissions. Some of the best ones got prizes, like cash prizes for their submissions. And these are a few samples of what we saw, right? We saw several simulations of the Mars helicopter. We saw somebody brought in the moon surface, and somebody brought in the ISS and docking into the ISS, the Enceladus. there were several connections to Isaac Sim, to NVIDIA's Isaac Sim, instead of Gazebo, which changes or affects the fidelity of the simulation, and also the visual appearance appears, at least to my eye, much better. We saw Viper, we saw Cadre, we saw Trick, a connection to Trick instead of using Gazebo or Isaac Sim. We saw someone implement procedural environment generation, so that if you want to generate a new environment, you can quickly do this procedurally, even if it's an environment that you perhaps it's not faithful to the data that we have collected. It is approximate, and it allows you to run experiments, and so on and so forth. These submissions are currently pull requests for the demo, for the demos repo that we have in the Space ROS organization. They're not yet merged, but the plan is now to work with the people who submitted. All the submissions are open source as well. So the plan is to work with them to merge some of these contributions. We'll probably merge some of them together and then into Space ROS. For example, we saw several submissions of the Ingenuity helicopter. They were very different. Some included smoke, some didn't. Some included like a control pad with a keyboard, some didn't. So we'll get the best of each one of those and work with the authors to see if we can merge those. But the idea is that it should be very easy for people to not just have a basic ROS system where they can start writing their software, but have an environment where they can start testing their system, and potentially an environment that is familiar or that is related to the mission that they're working on. Now, part of what Space ROS tries to address is providing assurance for robotics. And one of the biggest pushes, and especially originally in Space ROS, was in static analysis, in providing tools for static analysis of the code. Space ROS includes ICOS and Cobra, as well as other tools. ICOS is a NASA tool for static analysis. Cobra is a tool, it's actually not by NASA. That statement is, I believe, is incorrect. I believe it's a tool that was implemented by Gerard Holzman, but not, well, I don't know if he was at JPL. And I think he develops this currently through his company. But Space ROS includes both of those tools in the image, and you can run them immediately as you download the image. And you can also, once you install your ROS packages, by default, it will run those tools on your code and report any code violations. And there was also an exploration of other tools that could be used for code coverage and NCD testing, and we expect to do more in that regard. The tools were configured to produce RF output, which should be easy to parse by other tools. It's a relatively standard format. And the dashboard that I mentioned, which is a VS Code plugin, connects to the tools and connects to the Docker image and knows how to process serif. So it can take the portions of the code where you see violations reported by the static analysis tools. As I said, you can also run the tools from the command line. So just as you open the image, you have the tools installed and you can run them on your code. So it's not just a selection of packages, but all the processes, or sorry, all the tools that you need to provide assurance, or some of the tools you could use to provide assurance. Now, you already saw this morning that one of the big questions when it comes to flying systems in space is one of process compliance. And NASA has the NASA procedural requirements, which were presented this morning. And it's a long list. It's a very long list. Is there a question? I heard the mic on mute.
No, there was a bit of a good image to illustrate things. We got the attention of the people in the room.
It's scary.
You've got the attention of the people in the room. It was a good image. You're getting feedback. Nothing specific though.
Okay, good. All right. So I think I kind of coincided with the question that was asked this morning, which is, are there any requirements that are incompatible with open source? In that, it's not necessarily that the requirements are incompatible, but rather that the complexity of adopting these things is not practical to require an open source community project and outside contributors to go through this. To give you a measure of the resistance that we can find sometimes is in ICOS, which is one of the tools included with Space ROS, which is a static analyzer that we develop at Ames. Sometimes we get a pull request, and I ask the contributors, can you sign a contributor license agreement? Because NASA has that process. I cannot not do it. And they say no, because I'm not a lawyer. I don't know how to read this document and understand the potential implications, so I'm not going to do it. So even something like that, which is a relatively like if you read the document sometimes, I believe you can kind of get that all we're saying is you don't promise to maintain the code and we'll be able to relicense if needed, because, for example, we're trying to move ICOS from the NASA license to an Apache license. So it's something that we need to be able to do. Still, we find resistance for these things. Many of these requirements are far more complex than just potentially reading a form or something like that. And it would be infeasible to ask people to go through that. Unit testing, code coverage, MCDC, and so on. Also, it wouldn't necessarily serve any purpose, because what is at a specific level is not Space ROS as a whole, but rather the mission or the use of Space ROS in a mission. But what we have tried to do is we've come up with an initial lightweight process for compliance with some of these requirements. And the idea is we may be able to make it painless for anybody who has to evaluate how Space ROS is developed, whether some of those requirements are being met. We can make that job easier. And I'm going to highlight one requirement that is currently implemented in our contribution rules, which is the project manager shall track and evaluate changes to software products. So the way that we've kind of implemented that in our process is, well, branches don't cross. Whenever you make changes, always in the commit, reference the issue that you're working on. If there's no issue, then first create the issue, document what you're trying to address, tell us, is it a new feature, is it a bug? And that helps the technical committee evaluate the proposal, understand if it's something that should be included in Space ROS, if it's a bug, if it can be replicated, and only in that case, then the pull request makes sense to submit it and process it and so on. And all the commits need to tie to that issue, every single one of them, not just the last one, to make it very clear, to make a clear statement that this commit really is trying to address something about this issue. It doesn't address anything else. And so it provides that traceability from the changes in the code to the change requests in the tracking system. Of course, it doesn't go all the way necessarily to requirements. Space ROS is a community dynamic system. So we have kind of the goals, we have the change requests, and in the middle there's a little bit of leeway, but at least it provides a degree that there's not just random changes being added at will, but rather there's a process that we're following where we carefully evaluate what is being added. And the maintainers go through this process. Like if I submit a pull request to Space ROS, then somebody's going to evaluate it and approve it before it can be merged. And we also require, for example, that people clean their pull requests, that they don't just show us all the commits of how they figured out the solution, but rather they kind of not necessarily squash everything, but they tell the story in a way that we can process the pull request and understand what is happening and so on. And if we had to come back to it, we could figure out what's going on. So we have a process, an initial process. It doesn't capture all of the requirements that you saw. It tries to focus on just a few. The goal is to maybe address more in the future. But one thing that happened recently is that we added, well, this was Ezra Brooks from Picnic. He added scripts to the CI job to check that at least we are mentioning the issue in the commits. And the goal is ultimately to be able to analyze a lot more about this process automatically. And I'll talk a little bit about the tool that we can use for that. Yeah. So currently, we've published 5 releases at regular intervals every quarter for every 3 months. The next release is planned for January 2025. You're welcome to come over and contribute and participate. There's a few directions that we're pursuing because we have a large team of contributors. That also means that we're working in parallel on many things. One of the things that we're trying to do is simplify the development process and the implementation as a whole, make it easier for newcomers to start contributing. And we also rotate who publishes Space ROS and so on, so that everybody gets acquainted with the process and we get more feedback about how well that is being documented. There's currently an exploration of supporting other architectures, not just 64-bit x86. We're documenting that development and maintenance process. We're adding better integration with static analysis tools and VMV tools, and I'll mention something about that in a second. We're evaluating compliance with the NPR 7150. We're integrating, or we're planning to integrate some of the contributions of the NASA Spark Challenge. And we're also reaching out to the community. And last is, there's also interest in trying to merge some of the bridges to communicate with CFS and F prime. And we've had participants proposing to merge, or at least provide simulations that show how these systems function for both of them, for CFS and for F prime. Now, in terms of compliance, one of the things that we have done in the standards group, which is part of the groups that were at the beginning in one of the pillars, is we've gone through the 7150.2 and tried to understand if Space ROS can help through some of the tools or processes included meet any of those requirements. And if so, what documented what the element is. And kind of the idea is that this document is a living document, and it can help us understand what other improvements we could add to Space ROS in the future. So we can go to the document and say, hey, there's this tool that could help us meet this requirement. There's this other thing we could add. So let's work towards adding that to Space ROS so that people have an easier time complying with these things. I mentioned NASA only because of my background, but I think probably I would personally be very glad to see this being done for other organizations or for other processes that exist in other domains. And as part of a project called Copilot, which is a runtime monitoring project that we have at NASA, we've come up with a set of perhaps more stringent rules for compliance with NPR 7150. Copilot is developed at Class D, which was the original level at which the helicopter or F prime was developed, I believe. And but the code that it generates, it flies at Class C on a regular basis. It flies in drones at Langley and so on. And one of the things that we did was we developed scripts for a tool, an open source tool called Kayaulu, that pull all the data from GitHub. And they look at not just the commits, but also the comments in the issues, the comments in the pull requests. And they tell us if we're compliant with more steps of our process. So the thinking there, and one of the things that I want to bring to Space ROS is to make that process of compliance automatically. We cannot ask the open source community to figure out what our process is and then go through a complicated pull request review. But what we can is include those as part of the CI job, or give scripts that they can run locally very quickly that will automatically tell them, are you compliant? Or if not, this is a problem and this is how to fix it. These reports that come out of the tool are actually interactive, and they help us understand if we have any deviations in compliance. For example, these are deviations, or if we are acquiring too much risk. For example, these are two developers in the Copilot project that were taking most of the workload, and that meant if we lose one developer, we lose the core competency to maintain that code. Oops, sorry. And one of the things that I'm working on specifically is on trying to add runtime assurance capabilities for Space ROS. So we have this system called Copilot that generates runtime monitors that subscribe to the software bus, pull data, and check properties at runtime during the mission. And we're able to generate automatically from a specification of a property or even just natural language, we're able to generate a node for ROS that subscribes to the data that is needed by the property and notifies if there's a violation. So we could potentially go to the mission requirements, capture those, and then generate the ROS nodes. And this system actually works for CFS as well and for F prime. And the idea is that we could bring those into the future. Yes.
We're running past your time window. Do you have a couple more words to wrap up, and then we can move on? No,
Yep.
it's really, yeah, we just don't have enough time.
Yeah, no, you're fine. You're fine. It's fine. Just a last message I'll leave you with is that where we see this potentially connected with space-grade Linux is that even though the base image that we have is currently based on Ubuntu, we could potentially in the future build this on top of space-grade Linux. And on the one hand, it would provide a more comprehensive system that is space-graded. On the other hand, it would facilitate adoption of space-grade Linux because then you don't just have the kernel or potentially a distribution, but rather a full stack. And I'll leave you with that. You're welcome to join and come over and visit the organization and join the project and participate. And thank you so much for your attention. Sorry for going over time, but I'm happy to get questions later. And I'll read them in the chat.